So let me talk a little bit about the midterm, which is going to be next week. We're going to start at 7 o'clock, and the midterm will be an hour and a half. And I hate to do this, but after the midterm's done, I will have a lecture afterwards. I mean, if you mentally check out after the midterm and you want to go home, that's fine. But there will be lecture afterwards, just kind of introducing the next phase of our class. The midterm, I believe it's 35 questions long. It's going to be all multiple choice. Okay, I will provide the Scantrons for you and the exams, and you can write all over the exams. Please be sure to bring your reference tables and calculator and pencil and an eraser. And you're also entitled to a page of notes, but just the front side only. I don't know. What else do I need to say? Bring an ID. I have to do an ID check. I'm supposed to do that. So I think anything else about the midterm? Well, are there any questions? There's a page on the website that kind of just lists off most of the topics that will be covered. It's pretty much most of the topics we've gone over in class, but basically up through the stuff I do today. Okay, so today I'm going to cover confidence intervals for a difference in means, and we'll cover up to today's stuff. So basically from the start to today, and I think studying the quizzes will be helpful. That will there will be I don't know, some of the questions on the midterm will be similar to the quiz. Of course, the quizzes won't cover everything that's on the midterm, so study the other things that I've got listed on that page there. I don't know, questions? Okay, it's yeah, you get an hour and a half. In the past, I'd say about 80% of the students finished within the given time, no problem, and then maybe 20% or so would work until the end, and that's okay. So that's about it. Okay. So okay, so let me just go, I guess, cover confidence intervals again a little bit, and then I'll do a little demonstration on the computer to kind of explain what this 95% and all of that stuff means, and then we'll talk about confidence intervals for differences in means. Okay, so when we do a confidence interval, a confidence interval is kind of our first step, or I guess our introduction to what we call statistical inference. Okay, so at least in our class, this is our first method and what this means is basically we are using data and what we understand about I guess the theoretical distribution of data. So we're using data to make inferences or conclusions about a population that we want to understand more. Okay, so in inference we use data to help us understand something about our population. Okay. confidence interval, the specific thing that we're trying to understand about our population is what is the mean of a population. Okay, so the confidence interval we use a samples mean. Estimate the mean of a population. Okay. And inference, and basically the first 5 weeks of our course, we've been covering a few different topics. We've talked about just data and describing data, and we talked about some probability, and we talked about some distributions of data, like the binomial distribution and the normal distribution and all of that. Okay, and so it might have seemed a little bit disconnected, or just kind of like, here's a topic, and here's a topic. Okay, when we get into inference, inference builds off of all of those topics that we covered earlier. Okay, and even sometimes when we learn inference, we get caught up in the methods, and we forget, you know, why these methods even work. Okay, they work because of all of the stuff that we've done in the first half of the class. Inference stuff. In the first half of class. Okay, so far what we've covered is basically just describing data. We talked very, very briefly about gathering data, either through observational studies and experiments. Okay, so we talked about describing data and gathering data, and then we also had a separate topic which was on probability, and we had all of these rules about or and conditional this and that, and these but these were to yeah, we just had some rules on probability. Okay, and then we also learned about some distributions. Okay, and then we had the binomial distribution and the normal distribution. Okay. And after we studied these distributions, we built up the idea of a sampling distribution. Okay, and a sampling distribution, we didn't really get to show the theoretical side, but it builds off of probability and distributions, and we got sampling distributions. Okay, which are the distributions, not of individual points, but of samples, the sample mean. Okay, distributions. Sample means. So that's the okay. And so once we've established all of these topics, then we took our first step into inference with the confidence interval. Okay? And what we said is, you know, we understand something about sampling distributions. Okay? And the thing that we understand from sampling distributions is that when I take a large sample, the mean of that sample follows the normal distribution, which tells us that this mean of the sample will not stray too far from the population mean. Okay, that's the key piece that we took from the sampling distribution. Okay, so. Sampling distributions tell us the mean of a sample, or at least of a large sample, follows the normal distribution which means the sample mean is not too far from the population. Is that okay? All right, and with that, we created a confidence interval. So our confidence interval basically says, creates a zone of plausible values for our population mean, okay? And with a few caveats of just of using S rather than sigma, because the population standard deviation is unknown to us, so we use this sample standard deviation, and that means we had to adapt from the normal distribution to the t distribution. So after all of those things, we got our confidence interval to be y bar plus or minus some critical value t star times the standard error, which is S over the square root of that. Okay. And t star is determined by the degrees of freedom and the confidence level. Okay, and this was our first bit of inference, because here all we are doing is we're observing data. We took a sample, we have a sample of data, and we're using this, and we've created a zone of plausible values for the population mean. So this is our first thing of inference here. Okay. So later today, we're going to learn another inference method, and that's going to be confidence intervals for a difference in means. Okay. For a difference between population means. Okay. And here again, it's inference, so we're using data to help us understand something about a difference between population means. Okay. So this is what we're going to do today. I also kind of want to just give us a very brief outlook of what's going to come after the midterm, okay? And we're going to, so the rest of the class is all going to be just different inference methods, okay? And there's different situations for which our inference methods apply, okay? We didn't really talk about when this inference method applies, but just by the nature of this, this can only work when you have a quantitative variable. So a confidence interval for a population mean only makes sense when you've got a quantitative variable, right? Because you can't have a mean for anything that's not a numeric or quantitative variable. So this, you know, basically, this only works for a numeric variable. And it only makes sense if there's just one population that you're interested in, okay? If you've got multiple, I mean, if you have a bunch of different populations that you're interested in, you're going to have to create different confidence intervals for each one, okay? But this is just creates a confidence interval for a single population. Today, our inference method, again, will only work for numeric variables, but it allows us to compare two different populations, okay? This will be for numeric variables. Okay. And two populations. Okay. And what does it mean to have two populations? Or just think of an example where we might have two populations.
Different countries.
Two different countries, okay? Or men and women, or children and adults, okay? The United States or you know, Canada or something like that. We've got different countries, we've got different populations, okay? If you think about the different populations, what distinguishes one population from another?
Demographics.
Demographics, okay? I'm just going to be super general and say what distinguishes one population from another is just a categorical variable, okay? Just what your gender will distinguish one population, the men from the women, okay? Or yeah, your nationality will distinguish one population from another. So what we're really doing is we're comparing numeric variables based on a categorical variable. Okay, so two populations. This is the populations are distinguished by a categorical variable. The future of our course. Okay, so. Class. What we will cover is we are going to cover inference methods for numeric variables, and to see if there's basically a numeric variable and is there a relationship between the numeric variable and a categorical variable, okay? Numeric variables versus categorical variable. And we will start off with just two categories, but then we'll also work our way to 3 or more categories. Okay. So that's going to be a few different weeks. We're also going to be talking about, you know, what if we're not dealing with a numeric variable? What if we're dealing with categorical variables? Okay, and we're going to see if we can make inference on categorical variables in of themselves. Kind of like this is a numeric variable just for one variable only. Okay, and then we're also going to see categorical variables versus other categorical variables. Is there a relationship between different categorical variables? Okay, and then we'll also see if there's relationships between numeric variables. Okay, and that's going to be our last topic. So here we've got numeric relationships between numeric variables and categorical variables. Categorical variables by themselves, relationships between categorical variables and categorical variables, and then we'll also see relationships between numeric variables and numeric variables. Okay. So that's where we are headed. But today we're just gonna deal with, I guess, some more confidence intervals for a difference between population units. That's all we'll do. Okay. So let's just see if we can do a quick problem. So let's say we wanted to know what is the average what's the average number of licks it takes to get to the center of a Tootsie Roll Pop? Okay. Okay, so here in my generation, they had all these commercials of, I don't think kids these days would even understand this reference, but they talked about, you keep licking the Tootsie Roll Pop until you get to the center where there's a Tootsie Roll on the inside, okay? It's a lollipop. And, well, let's say there was some, like an experiment where you could accurately do this, right? Because normally you just stick the lollipop in your mouth, and after a few minutes, or if you bite it or whatever, you get to the center rather quickly. But let's say we found volunteers and we trained them on the proper way to lick the lollipop and count, and we controlled all of these variables because we want to do an experiment and we want to get accurate data, right? If you get junk data, all of your analysis is going to be junk, okay? But let's say we properly designed a way to count licks, and we got a bunch of volunteers, and let's say they said one person, this is the data we gathered, and let's say somebody said it took me, I don't know, I have no idea what a good number is, 68 licks, okay? And someone else says, oh, it took me 84, and someone says 73, and someone says 108, and someone else says maybe 50's too low. I don't know. Okay, we'll just leave 50, sure. Okay, so let's say these were the numbers we observed. Okay, and let's just say this is a random sample. Okay, these numbers represent a random sample. Well, to be technical, it's not really a random sample because, I don't know, we had to find volunteers, train them on how to lick the lollipop. But there's no reason to I don't know, question that these numbers might not represent the general population, okay? Alright, can I make a confidence interval based on this? Based on these numbers? Yes, no? So this is just a sample that I observed, right? So this is here's a sample, this is a sample I observed. Okay, based on this data, what can I say about the true average number of licks it takes to get to the center? Can I say anything? Do I need more data? Or do I need to do something?
More data.
More data? Okay. Yeah, I mean, probably more data is better. Usually, the more data you can collect, the better you'll be. But I would say this is okay. We can use this. Okay. And so the answer is, yeah, we can use this and we can create a confidence interval. Okay. So so let's make a confidence interval. Okay. And you're absolutely right that here, we've only looked at 5 different people, and they licked the Tootsie Roll Pop, and this is what they reported. But ideally, we would have more than 5 people. But just for the sake of this, I just picked 5 numbers. Okay. So what would my confidence interval look like, and how would I do this? Okay, so just to refresh your memory, I'll put the formula for confidence interval back. Y bar plus or minus T star times S over the square root of n. And let's say we want to make a 95% confidence.
You need to find the standard error.
Okay, I gotta find the standard error. How would I find the standard error?
Well, wouldn't your n equal 5?
Okay, so my n is equal to 5. What else do I need? I need a standard deviation. Okay, do we know how to do that? Yes? Okay, right, we have to find the mean first. So we gotta find the mean, so I add up all 5 of those numbers, 68 plus 84 plus 73 plus 108 plus 50. I divide by 5, I get 76.6. And then I have to subtract 76.6 from each of these numbers, square them, divide by 4, or square them, add them up, divide by 4, and then take the square root. And then that would give me the standard deviation. A little bit of a pain, but certainly not impossible. Okay, but I'm going to just take a shortcut, and I'm going to ask R to do the work for us. 68, 84, 73, 108, and 50. And R says the standard deviation is 21.42. Well, there's a few more decimals, but that's close enough. All right. And what is my T star? degrees of freedom do I have?
4.
Degrees of freedom is 4. N minus 1. So that at 95%, my critical value T star is 2.776. Alright, so this, because I only have 5 data points, my my confidence interval is going to be close to worthless, but we'll make it anyway, okay? 76.6 plus or minus 2.776 times 21.42 divided by the square root of 5. So let's do that. 21.42 divided by the square root of 5 times 2.776. So I have 76.6 plus or minus 26.6. Okay, so on the lower end, 76.6 minus 26.6. That's 50 exactly. And then on the upper end, I have 103.2. Okay, so my 95% confidence interval goes from 50.0 to 103.2. And so that says I am 95% confident. I am 95% confident that the average number of licks to the center of the Tootsie Roll Pop center is between 50.0 and 103.2 clicks. Okay. So that, I mean, that's a very wide interval, and that's largely in part because we only have 5 data points, and also because the standard deviation between the different licks that we observed is quite large. Okay. If all 5 people took the number of licks it took them to get to the center was like 62, 63, 65, 61, then our confidence interval would be a lot smaller because the S, the standard deviation itself, would be very small. Okay, and so our what we call the margin of error would be small. But here it's quite large, so we've got quite a wide range of how many licks it might take to get to the center. But it still tells us something, right? Does this confidence interval provide evidence that the number of licks it takes to the center of a Tootsie Roll Pop is not 25? Okay, so I mean, it is theoretically it's possible that the average is actually only 25, but this provides pretty good evidence that it's not 25. Okay, why? Because 25 is not in the interval. So numbers like 25 is not in the interval. So our interval, or our data, provide evidence that the average number of licks not 25. But if the average, it doesn't mean it's impossible, okay? It just provides evidence that it's not 25. If the average number of licks is 25, then what happened?
Got a really talented sample.
Yeah, if the average number of licks is 25, I got a really unusual sample of people where the number of licks was extraordinarily higher, okay? And like probabilistically impossibly high, okay? But that's what would happen, okay? Or that's what it means. So anytime we create a confidence interval, we're not stating a probability of the population mean. It's not correct to say there's a 95% probability that the average number of licks is between 50 and 103.2, okay? Because the average number of licks it takes to get to the center of a Tootsie Roll Pop is some number already determined, okay? It's set at some number that we don't know, so it doesn't make sense to talk probabilistically about something that's fixed. But our sample is random, and anytime we take a random sample, based on what we understand about sampling distributions, okay, that says, based on that, we can say we're 95% confident that the population mean is in this range, but it's also possible that it's not. And I wanted to illustrate that a little bit with kind of a computer demo. Let's try this. Okay. So I'm going to just copy a whole bunch of code here. This used to be a lab, or I mean, this is a lab that I've assigned, but then now I'm questioning the usefulness of this lab to have you guys do it on your own. I like it, but I'm just a bit okay. Let me, all right, so this is, let me just explain what's going to happen here. Here's a histogram that I've turned on its side, and this represents a normal distribution here, okay? So this is a normal distribution, and this represents our population. So what I'm going to do is I'm going to demo how creating a confidence interval works, okay? So I'm going to pretend that I've taken maybe 10 randomly selected points out of the population, okay? And so the mean is 0, and it goes from, so I might get some points, like I might get 2, I might get 1, I might get 0.3 or negative point something, okay? So I'm gonna get 10 dots, and they're gonna just show up in a column, okay? And this is gonna be like our first sample. We're gonna graph 10 dots, and that's going to represent the random sample of 10 that I've taken from the population. And then what you'll see after that is a blue dot is going to appear, and that's going to represent the mean of the 10, the random sample of 10, the 10 random points that I selected. Okay. And based on that blue dot and the sample, okay, R is going to, inside itself, it's going to calculate the standard deviation and the standard error, and it's going to create basically a confidence interval. Okay, it's going to create a confidence interval, and it will graph that. So let's just do this once. It's actually. I'm going to slow this down a lot here. I can just make this a little bit bigger because it's. Okay. So, okay, you can barely see it, and I put it over here. But what it's doing is these circles represent the dot, the random sample of 10 points that I selected. The blue is the mean of the 10 dots, and this is the confidence interval that it's created. Let me just do that again. So here it's there's another random 10 points. The blue is the dot, and then it creates a confidence interval. Okay. So let me just do a whole bunch of these. So let's do 10 of these, and I'm gonna just speed this up a little bit. And you're gonna see the process repeat itself about 10 times. Each time it's gonna select 10 random points, calculate the mean. So 10 random points, the mean, confidence interval. 10 random points, the mean, confidence interval. 10 random points, the mean, confidence interval. 10 mean interval. 10 points, mean interval. 10 points, the mean interval. 10 points, the mean in the interval. 10 points, the mean in the interval. There we go. Okay, and we can see that sometimes the 10 points that we gather are rather close together. Okay, so here the 10 points all range from about -1 to maybe 1.5. Okay, so there wasn't a huge range here, and the mean was right there, and so you can see the width of the confidence interval, because the standard deviation of the sample was not very big. The width of the confidence interval is not huge. On the other hand, we have some samples where there's quite a large, quite a bit of spread or standard deviation within the sample itself. And so we've calculated the mean here, but you can see the width of the sample, width of the confidence interval is a lot wider. So this interval is pretty wide, this interval is pretty narrow, okay? This one's pretty wide. And so some intervals are more narrow and some are wider, and it depends on the sample itself, okay? So of course, this would not happen in real life, because if you could afford to take a sample of 10 times, you would just take one sample of 100 and combine all of your information together. But by having a computer and being able to run simulations, we can kind of understand how anytime you take a random sample, okay, if you got a random sample of 10 points, you have no idea if you got this one or if you got this one, okay? And sometimes let me just speed this up a tiny bit. And let's try taking a few more of these. So this graph might get a little bit more crowded here. Okay, but I'm going to create 25 of these different things. Each time it's taking a random sample of 10 points, figuring out the mean, and creating a confidence interval. And let's see if any of our confidence intervals don't work. get lucky in that every single one of these confidence intervals that we created crosses the mean. So the mean is represented by this horizontal line at 0, okay? And every single confidence interval that we created includes 0 within the interval. This one almost missed it, okay? So the sample that we took happened to get a bunch of positive values and hardly any negative values, okay? And so when we created the mean, it's all the way up at 1, and when we create the confidence interval, it barely touches 0, but it does, okay? And so our confidence interval is like from 0 to 1.8. That's what it's guessing to be plausible values of the population mean. But it includes the population mean, okay? And so whenever we take a random sample of 10 points, or whatever sample we get, we don't know if we get, this one, where the mean of the sample, this blue dot, is very close to the population mean. We don't know if we're this sample or if we're this sample, where the mean of the sample is pretty far away from the population mean. Okay, so when you observe a random sample, you have no idea what this sample, how this sample compares to the actual population. Okay, you can get a sample mean, but you have no idea if this sample mean is anywhere close to the population mean. You're just kind of counting on the fact that on the random nature of samples and our understanding of sampling distributions, that the sample mean is not going to be too far from the population mean. Okay, but I'm trying to get one where it messes up. So let me just try this again. Okay, so last time I ran 25, and all of them happened to contain the population mean. This time I ran 25, and 2 of them, which is this one, when we created the confidence interval, it missed the population mean. Okay, just by a little bit, but it missed it. So here the confidence interval goes from like 0.02 or 0.01, maybe up to about 1.4 or something. But here it says, I'm 95% confident that the population mean is between 0.02 and 1.4. But that confidence interval is wrong. The population mean is 0. And so this thing did not include the true population mean within the range. Same with this one. This one also missed it. Okay, and again, whenever we take a random sample of size 10, we don't know whether we got this one or whether we got this one. Okay, and sometimes there's a tiny, our sample is quote well behaved, or there's hardly any spread, and so our spread confidence interval is very narrow. Okay, and this might give you and actually misrepresent kind of the spread in the population, but here we're just concerned about the mean, and this is what we get. So you have no idea which one of these samples you are, but you're kind of hoping. So we saw a total of 50 samples, and 2 of them failed. Okay, and that actually makes sense, because this is a 95% confidence interval. So 2 failures out of 50 is about 4% failure, and so this represents, from what we've seen, about 96% of the 50 confidence intervals that we generated contained the population mean, and 4%, or 2 of them, did not. And so even though you have no idea whether you are this sample or this sample or this sample, you're kind of counting on the fact that based on the properties of randomness, your sample is quote well behaved and is going to be one of the 95% that contains the population mean, and you're hoping that you're not one of the 5% that missed it. when we alter the confidence level from 95% to 99% or 90% or whatever, you can see that the T star, the critical value T, gets larger when you increase the confidence, and it gets smaller when you decrease the confidence. And that just means, all you're doing is you're saying, if I want to be more confident about capturing the population mean, I have to make my zone of plausible values wider, because I want to just be extra sure that I've got the population mean in here, right? So it's just like if your friend says, oh, how much money should I take to the baseball game if I want to get something to eat? In your mind you might say, oh, it takes, you might need about $15, but just to be safe, better take 20 or something like that. Okay, so we do this all the time in our own life. We say, okay, just to be safe, if I want to be extra safe, I'm just going to pad this and give myself more room. And that's essentially all we're doing here when we change the level of confidence from 95% to 99, or some other level. We're just padding the confidence interval by making it bigger. Okay, but you can see the jump from 99% to 99.9% is a pretty sizable jump. Okay, because being 99.9% leaves almost no room for error. That means only about 1 in 1,000 samples will throw you off. So you're making this very wide confidence interval, but it's almost to the point where it's ridiculously wide. Okay, or just a little bit too much to be practical. Okay, but sometimes with issues of safety, they want to run like a 99.9% thing. Like airplanes, they want to be like 99.99%. Okay, because it's the idea of failure is so catastrophic that they don't even want to risk 1/10 of a percent. Okay, it's like 1/100th of a percent or even less. Okay, so that's okay. Does that make sense? And I guess in the lab you can. I'm debating if I even want to assign this. You can try changing the shape of the population and see how that affects the confidence interval. So this is the population that's assumed normal. You can see ones that are skewed, and it's gonna mess with the properties of the confidence interval as well. And we can increase the number of points that are selected. So rather than 10, we can select 100 random points. And what we'll see is that the confidence interval gets a lot more small, okay? Much more narrow. Okay, let's take a short break.